Next speaker is getting ready, and he's going to tell us about Lagrangian multiforms, a variational criterion for integrability. Thank you, Vincent.
Okay, good afternoon, everyone. Can you hear me with the microphone? Yes. Thank you so much for having me in this great place for a wonderful program. So I have the hard task now to give a talk that contains very few pictures as compared to a whole day of beautiful movies and amazing plots. I only have 3 pictures, but you'll see that they're amazing. Let me see if that works actually. Maybe not. Oh no, it's not been plugged. Well, it's okay. I'll do it old-fashioned style. Yeah, so it's a topic that's not very well known at all because it's quite new, relatively new, and essentially the people you see on the board, the collaborators, plus a few others around the world, are the main ones that contributing to the topic so far over since the original paper in 2009, over the last 4 or 5 years, a bit more intensively. So there's Frank Nijhoff in Leeds as well, 2 former students, Duncan Slay, Matteo Stapato, a former postdoc, Mats Vermeeren, who's now in Loughborough, and Benoit Vicedo, who's in York. Because it's quite new, and the idea is actually to look at some of the foundations of our beloved area, which is integrable systems. I'm going to start from scratch, Hamiltonian and Lagrangian mechanics, and sort of bring you to the question, the problematic, and then show you some of what we've done. So yeah, that's part 1, the general context. Then the key idea to answer the key problem. And then put the hands in the problem, and how do you actually construct this thing called a Lagrangian multiform. Once I will have told you what that is about, and then give some perspective, hopefully, that circle back to the theme, one of the themes of this workshop, which is generalized hydrodynamics. So here are my 3 amazing pictures. Right. So yeah. Lagrangian, Hamiltonian, if both still survive nowadays, is for a good reason. That's, they're powerful and they both bring something to the game when you want to describe some dynamical system. So I present this a bit as a fight between the 2, because actually some people view it like that. My own view is that no, you should really use them in combination, and because one always tells you something that the other one cannot tell you. History has shown that when one seems to win, the other one comes back with a vengeance. One famous example is, canonical quantization at the earliest 20th century, and then Feynman came and said, no, Hamiltonian is not the full story. Lagrangian is also very powerful. A review, set the scene, hopefully so that everyone is on board. If you think about finite dimensional systems, mechanics, you can decide to model them and their evolution with Hamiltonian formalism. So you have a phase space and then a particular function, which is called the Hamiltonian. These are the Hamilton equations for such a system. If you also possess a Poisson bracket, you can rewrite that very nicely. The fact that you have a Poisson bracket also has all sorts of very nice implications, geometrical implications, but I'm sure anyone knows about that. It's just to set the scene. And alternatively, you can describe a system using the Lagrangian formalism. And here, actually, and ironically, you have the Hamilton principle for an action, which tells you that the dynamics of the system would be obtained among the critical points, or stationary points of this object. So here, this is the Lagrangian function. And you demand that it is stationary, and that gives you something called the Euler-Lagrange equations, which is the content of the next slide. So, right, there's some private discussion going on. So yeah, one of the fundamental results in the Lagrangian setup is that the analog of Hamilton equations are given by the Euler-Lagrange equations, and well, there's a quick show of the proof that you've all seen. So if you have a Lagrangian only linear in the velocities, sorry, depending on the velocities only, the key part is that you have an integration by part step, and you require that this is 0 for all possible variation with fixed boundary values. So the boundary term typically vanishes. That has to be 0 for any arbitrary variation. So you get the Lagrange equations. So far, so good. No integrability so far. Okay, that's completely general. And this is where things start to be very imbalanced because the very terminology integrable and integrability actually has its roots in very old work, which is set in Hamiltonian. So the roots of the name integrable is in the Hamiltonian formalism. In particular, now people call it Liouville integrability because the terminology has evolved and people talk about integrability sometimes when you only have Lax-Baer formulation. Obviously, one of the fundamental results is that if you have a Lax-Baer formulation, usually it has a Hamiltonian formulation, well, in all cases, hence the origin of the terminology. And there, the idea is that if you have an n degrees of freedom, and you can find n functionally independent functions on the phase space that Poisson commute pairwise, there is a change of variable, a canonical change of variable that completely linearizes your dynamics. This is the Liouville-Arnold theorem, which is very well known. One important consequence is one of the main messages today is that when you have this collection of functionally independent functions, Hamiltonians, you can actually embed your original time flow into a family of time flows. Each is described by its own Lagrangian, Hamiltonian. Lagrangians are not here yet. So you see the original time I had, the unique time associated to my particular Hamiltonian actually becomes just one of n. And the reason why I'm allowed to do that and to impose all these various time flows simultaneously is precisely because of this property that they Poisson commute, which implies that the corresponding vector fields commute, which implies more visually that if you start from some initial point in your phase space and follow the trajectories along various times, the path doesn't matter. You will arrive. So it's a path independence. That's what this condition captures on your, what I call multi-time. And the key message here is that actually your single system, for instance, Annalisa or KDV, that you can view on your own, from this point of view, it's much more efficient to view it as just one of many in an integrable hierarchy. And doing that, you reveal a lot more structure about why things are integrable. And that's the idea that we've used essentially in the Lagrangian counterpart, is to think not of just single system, but to think about the entire hierarchy that it lives with. That's the main idea. So now, if I want to formulate a criterion for integrability using only Lagrangians, suppose I don't know anything about Hamiltonians. Well, as I said, so now you have your single Lagrangian that describes your preferred theory, and you're like, well, there's already a first problem, because if the Hamiltonian picture tells me I should have n Hamiltonians, I only have one Lagrangian. So you can say, yeah, no, but it's fine, because if I have my Lagrangian, I can construct, and I know symmetries, I can construct the concept charges, and those concept charges play the role of those Hamiltonians. But then the picture is a bit wobbly, because you have one Lagrangian and n-1 Hamiltonians. And you still don't really have a criterion to encode integrability. So it's not satisfactory at all, this Noether charge point of view. And there came the key idea in 2009 by Frank and his PhD student at the time, Sarah Loeb. They formulated an idea. So if you look at the paper, you will not recognize any of what I'm going to present today, because it was done in the integrable system discrete context. But actually, the key idea was already there. And then what we did is transpose it in continuous setup. And what is the idea? Well, we only have one Lagrangian and an action, but we need more. So let's propose an action that is more general for a more general object, not just a single Lagrangian. And we've heard a lot about generalized things this week. So, okay, so generalized hydrodynamics, generalized Gibbs ensemble, where we're going to have our own generalized variational principle. And you'll see at the end, maybe they talk to each other. So in equations, the top part is traditional action. So the Lagrangian, the square bracket, it means that it depends on positions, velocities, high acceleration, if you like, it doesn't matter. It can be very general. And now you replace it by a one form, so a collection of Lagrangians. So all these L1 to Ln are some Lagrangians, and I associate to them a time, like I would do a bit from the inspiration I would have from the Hamiltonian system. And at the moment, they're just coefficients, unknown coefficients for some theory, would be integrable theory. And the new ingredient is now this gamma is a path on this multi-time. So before it would be just an integration, you know, over one time. Now it's a path on this multi-time. And if you think about what I said that about path independence, what we're going to do is propose a variational principle that captures this path independence. And that's the trick. So a bit of explanation. I think I explained already. Yeah, essentially, yeah, I explained already the structure. So now the step 2 propose this generalized variational principle as an integrability criterion. So before we had this Hamilton principle, which is to say the solutions of my theory are the critical points of my action. So you'd say the same thing. Solutions of my theory are critical points of that new action, no matter what gamma is. So that's where you plug in the path independence. So no matter what gamma you choose, you should minimize your action. And second, so you will see that actually selects Lagrangians very strictly already. So you're almost there. And then the second thing is that on shells, we're going to require that the value of the action, when you calculate it for one of the allowed configurations, actually does not depend on the path. It's the same. And if you do that, let me show you some of the consequences. So if you do that, you get a generalizations of the Euler-Lagrange equations, which we call multi-time or multiform Euler-Lagrange equations, and they come in 2 sets. The first set is your traditional Euler-Lagrange equations, but for each of the Lagrangians and its corresponding time. So at the moment, it's like you have n independent Lagrangians. So they don't know anything about each other yet. But that's because those arise when you look at gamma along one of the TK directions. And now we're going to require that actually it doesn't have to be one of the main directions TK, but as I said, it should be parameterization, path independent. So now they're going to start to talk to each other in a non-trivial way. And that's the second set of equations, which traditionally are called corner because in a discrete setting, they come from cubes. So they're corner equations. And now these ones are the new key ingredients. So they control the structures of your allowed Lagrangians. So the idea, the philosophy now is like those Lagrangians that I don't know anything about, in principle, you could use these equations to classify them, and you're guaranteed essentially to have an integrable model. And if you want to know what the equations are, well, you plug in whatever you found from these equations in the Euler-Lagrange equations, and that's the equations of your model. So that's the new feature. There's a constraint on the allowed. You can't just put anything, which you would expect from integrability. I'm coming to that because that's the punchline. And then the consequence of the second requirement, so the fact that you should have the same value on solutions, and that's the key, on solutions, no matter what the path is. There's a geometric interpretation. It comes at well, you have a closed form, essentially, a closed one form. And in components, it gives you this condition. And that's the one that you have in mind. That's the one that corresponds to Poisson commutativity of the Hamiltonians on shell. So exactly, why would that be a good criterion at all? You know, you have to well, you can believe that it's a good criterion, but you also have to convince other people. So there's lots of reasons why you should be convinced. But yeah, the punchline is really this equation. So the closure relation, when you do the Lagrange transformation, is equivalent to the Poisson commutativity, which is an accepted criterion since Liouville. So let's not dispute that. So the takeaway message, yes? In what sense?
So
oh, yeah, yeah. So typically when you construct solutions, the already from the kinetic part, you'll see that they're functionally independent. I mean, it's not embedded in the equations, but so it would be something you have to check once, if you ever have examples. But then in all the examples that we've built so far, this is the case. Yeah, it's not a theorem, if that's what you're after.
Your construction doesn't. Maybe I can inform it that your equations do not force the associated Hamiltonian to be functionally independent, or do they?
Right. To think now. Yes, they will be functionally independent for the good reason that a Lagrangian with index k related to the k cannot depend on the velocity along j, whereas the Lagrangian along j will depend on that velocity, and they're independent coordinates. So yeah, that's built in the construction. Thank you. Actually, I never realized that. Okay, so all these ideas that are presented in the simplest setting of classical mechanics, if you like, they're generalized to field theories, 1+1, which is what I'm going to focus about today, but we also actually have an example in 2+1, which is KP. Yes?
Like the derivatives with respect to other times,
but if you think about the tangent space now, it spans by more velocities. Yeah. So you span a lot more directions. Yeah. So from this point of view, they become yeah, no. Now you lift to a height because your base manifold is higher dimensional. Yeah, it's not just T, it's Rn. Yeah. So you you need to specify the initial velocities along all the directions. Yeah. Yeah, you generalize for field theories, and then you just keep the recipe. The only thing, the technical thing, is that an action, a traditional action now would be a volume form on a surface. So you integrate an action on two-dimensional space-time. So now the object, instead of being a one form, becomes a two form, and you get all the times of your theory. And because it's an infinite dimensional theory, in principle, you have an infinite number of those times. Again, the sigma plays the role of this arbitrary path that we had before. Now we have an arbitrary surface in this higher dimensional time. And we're going to require, same thing as before, you require criticality no matter what the surface is. And you're going to get two classes of equations, standard Lagrange, and the new ones, the corner that constrain the possible Lagrangians that you're allowed to have. So I've already summarized the next. So yeah, you propose the generalized variational principle, which is the same story as before, but adapted in 2 dimensions. And with the similar consequences, the equations are more complicated, so I didn't write them down by lack of time and space, but they're written down. There's actually a nice compact formulation for them in terms of something called the variational bicomplex approach to variational calculus, which is coordinate independent. So it's very nice, a single formula. And the second requirement, again, we have a closure relation, which now takes this form of a cyclic permutation on your coefficients instead of having just the cross derivatives of a one form. So now that's the three form analog, because you have the differential of the two forms should be 0. The reason why I insist a little bit, because that's going to come back later. So remember this cyclic sort of structure for the closure relation, which is the key, one of the key features of the integrability criterion. On the solutions. So to show that this holds, you use the fact that this field U satisfies the multi-dimensional Lagrange equations that you derive in the first step. Okay, so again, why is it a good criterion? Well, we have now quite a few examples actually that show that the theory is not empty and actually captures integrability in a nice fashion. As I said already, in a finite dimensional case, there's a nice link between the closure relation to the Poisson commutativity. It survives in the field theory case, but then it's a lot less natural. I don't have time to talk about that because it would be another talk altogether. But these Hamiltonians that you use in field theory, I don't like them because they're non-covariant. But there's a way to define covariant Hamiltonians when you have a field theory. And then if you do that, your zero closure relation in terms of these covariant Hamiltonians takes the same cyclic form. And I would like to argue, I don't have a proof, but to me, this is the correct generalization of this in finite dimensional mechanics, where this holds. But the only issue is that we don't have a Poisson bracket analog of this characterization, but in classical mechanics, we do. So I've been thinking about that because there's also a notion of covariant Poisson brackets, but that's for another time. Anyway, so that's kind of an aside. Yeah, so I mentioned there's a problem. So why is it a good criterion? Also, the latest results for me, which I can see the bottom, which is more fundamental, is that the closure relation, which I hope I conveyed, is the important criterion because it's the analog of this Poisson commutativity, is related to the classical Yang-Baxter equation. So the classical Yang-Baxter equation is the classical counterpart of the quantum Yang-Baxter equation, which at least I hope you've heard the name in integrable systems, is very, very fundamental. So to me, that's a good signature. So, and I'm going to try and convey this. The reason we came to this observation that it's related to the classical Yang-Baxter equation is because then you have a practical problem of constructing examples, right? It's all nice and say, well, you can do this, you can do that, then you need examples. At first, so the first few years, we didn't have this hierarchy point of view so much. So what we were doing is trying to construct the higher Lagrangians from knowing only the first one. So for instance, you know the Lagrangian for NLS, and then you know some of the symmetries, and you say, okay, let's construct the next one, and then so the L13 and then the L23, and by trying to solve recursively these equations, then we got a little bit more clever, and we used the idea of variational symmetries and the theorem, but it was still recursive and very technical and difficult. So let me show you an example, actually, because there hasn't been an example yet. So that's what I was explaining. So imagine you take your AKNS hierarchy. So we've seen the nonlinear Schrödinger a lot of times already. You may not recognize it yet immediately, but it's there in its unreduced form. So if I say that the field R is related to the complex conjugate of Q, these two equations become the same. 1 means double x derivative, 2 means t derivative. So that's essentially your NLS. And with the same token, that would be your modified KTV, the next one in the hierarchy. So imagine I know only these two things, and I compute the Lagrangians for them. The Lagrangians are known. Okay, so you just take them. Then the next step to construct a multiform is I need the Lagrangian for time 1 and 2, or time 1 and 3, and to complete the trinity, I need the 2 and 3. And then you're like, how do I build that? So brute force, when you have a good student, you know, and then they come up with this formula. We are none the wiser, but it works. Say, okay, it works. So I'm not going to comment because I don't know what to make of it, except that it works. And it's the compatibility of all the flows. So then say, okay, let's let's just guess, right? So there's a lot of things why I came with this guess and a lot of inspiration, and I'm just going to give you the results at a time and try and explain what it means. One first idea, again, putting things in generating functions. We've seen that idea before in this week. So the key that you want is these Lagrangian coefficients. Whether they're in a two form or on their own doesn't matter. So then let's package them in a generating function of two spectral parameters, because we like spectral parameters in integrable systems. That's where you see the structure. And then you just give a formula and check that it works. So here's the formula. It's a nice Lagrangian. It's got a kinetic part and the potential part. And now it's a bit less nice. So that's the kinetic part. That's the potential term. And now you're like, oh my God, what is going on? So let me comment a little bit. So lots of ingredients. So first of all, this function f. Function f is just some rational function with given poles, with some in the sphere, and with values in some Lie algebra, but thinks just a matrix valued rational function, fixed. Second ingredient, package all the flows in a generating function as well. So that's what these derivatives means. Actually, this is all the flows, the partial derivatives packaged using this generating function idea. So I'm working with formal series, power series, but no problem with that. Third ingredient, and that's the key, that's the fields of the theory. And the idea comes from dressing, or formal dressing ideas of this bare lax matrix, if you like. That's actually your bare lax matrix. You dress it with your fields, and you get the fields of the theory. So you can work either with those fields which are in the group, or with those ones which are in the Lie algebra level. You can show it doesn't matter. It's a matter of preference. Don't worry if that doesn't mean anything to you. It just means there's a way of constructing the fields, right? And the last ingredient, my favorite ingredient, is the classical R matrix, which determines which type of model you want to encode. So there are three types, essentially: rational, trigonometric, and elliptic. Again, if you don't know anything about that, it just tells you what class of integrable models you're working with. And there are some notations, etc. So these are my ingredients. And why is that a good Lagrangian to look at for an integrable theory? And then again, lots of reasons, but the punchline is that you take your coefficients, LJK, you compute the corresponding Lagrange equations, they're equivalent to your zero curvature of all the hierarchy. So that's where your equations of motion are in the form that we all know, zero curvature for a lax pair. And our approach also tells us how to compute those guys from our data, from the fields. That's, to me, that's the key statement. And so far, it's very, very general. Also a note, I think it's not very largely known that zero curvature equations are variational. Yeah, they are Hamiltonian, so they are variational. Okay, and the main result I was telling you is that the closure relation is a consequence of the classical Yang-Baxter equation. So again, that doesn't mean anything to you, it doesn't matter, but that's a key signature of integrability. How do you construct the examples? You fix a small amount of data. Fix this function f, so your bare lax pair with poles. Fix your Lie algebra, fix your classical R matrix, and then spit out models. So you can do the AKNS, that's the simplest example. Then you recognize the theory. Reproduce sign-Gordon hierarchy, some rational trigonometric Zakharov-Mikhailov models, which are a large class of generalization of principal current models, etc., etc. So it's sort of plug and play. You can construct whatever you like, and every time you get the whole hierarchy. Okay, and one example. Let me skip that, because you can do new things. It's not just recovering old models. You can actually create new models by coupling them. But let me skip that. And because I want to spend one last message, say, okay, so what? We're having fun. we're constructing things, but for this audience, maybe some of you are like, yeah, okay, you're having fun, but what's going on here? I just want to, this is extremely speculative, but I think there's something to it, because the top line is a known connection between the Gibbs ensemble approach to thermodynamics that has been discussed, and the path integral built on an action with some trick. You go to Euclidean, and then you take a periodic time. And we've heard a lot, as I said, about generalized Gibbs ensemble, but now we have generalized action and generalized variational principles. So my proposal is, can we make sense of such an object, calculate things as a complementary approach to what has been discussed by Benjamin and many others? And you might say, no, let's not do that. Path integrals are notoriously horrible. You can only do them perturbatively. Let's forget about it. But that's because if you look at general theory, they're not integrable. But as always, integrable theories are special. And the Lagrangians that we found, they have a very, very special structure, which I've realized recently appears in a completely disconnected theory of so-called coadjuvant orbits methods of Kirillov and Frenkel, which allow you to compute things that are actually a bit like this. So I think I'll finish on that. There's a lot to think about. So it's not just a fancy abstract tool. I think it could also perhaps bring something to the game some of us are trying to play here. And on that, thank you very much for your attention.
Is there any question?
Thanks for the talk. What would that mean to have a continuous symmetry in your Lagrangian multiform formalism?
Right. That's a question I've been asking Frank, and at the time I PhD student said we need to look at that. Right. So I think the natural symmetries of such an object should be gauge transformation, in the sense of gauge transformation of the underlying Lax pair, which have an interpretation in terms of Poisson-Lie transformations. So there's again, because the R matrix is in the game, and the R matrix is kind of one of the key objects behind this Poisson-Lie approach, they should be in there. So I think that's the idea, but that's something I want to look at, because that's something I haven't understood yet. But then the natural thing to look at is gauge transformations on this field phi at the group level. That's what you should look at. But then how do you correct? I think in the symmetries you see should be dressing transformations in your hierarchy. But these are just words at the moment from an intuition. That's one open question, one of many.
So does it give you a way to think about integrable systems with holonomic constraints?
I don't know.
I mean, usually it's like you start with Hamiltonian and it's hard to figure out how to constrain the system. But if you have the Lagrangian, you just put
there you put some Lagrange multipliers, extra
Correct.
Lagrange multipliers.
Yeah.
Yeah, possibly. Yeah. The short answer
In all
is
the
why
flows
not?
at the same time, I guess.
Yeah.
All right, let's thank Vincent again. And we are resuming at 4 and we have a coffee break.
Oh, okay. Yes. Oh, sorry. No.
Your very last slide, so you put very C to beta H. You had some quantum mechanical model in mind. For your generalized Gibbs.
Yes.
So which H do you want to take?
Well, to warm up, I would take something that is finite dimensional, so possibly a Calogero or yeah.